Welcome back to the Deep Dive. Today, we're doing something a little different. I want you to take everything you think you know about the Titanic, the James Cameron movie, the violins, the romance, all of it, and just for a little while, put it aside.
Right.
Because today, we are not telling a ghost story. We are, in effect, conducting a forensic autopsy.
That's the perfect way to put it. It's time to strip away the century of mythology. We're going to look at the Titanic not as a legend, but as a massive, complex crime scene.
A cold case.
A very cold case. And like any cold case, when you apply modern science, and I'm talking about 21st century metallurgy, atmospheric modeling, high-resolution 3D scans, the story you thought you knew, it changes completely.
It really does. And for this deep dive, we have an absolute mountain of sources. We're not just relying on survivor testimony from 1912, which, as we'll find out, is it's often contradictory.
Understandably so.
Exactly. No, we're looking at government reports from NIST. That's the National Institute of Standards and Technology. We've got the actual metallurgical files from Dr. Tim Folk, who put the Titanic's rivets under a microscope.
Really groundbreaking stuff.
We have historical debunking from historian Tara B., atmospheric research from Tim Malton, and then transcripts from these incredible new 3D scan documentaries that are mapping the wreck like never before.
And the mission, really, for us today is to answer that one question that has just haunted maritime history for over a century. How did the largest, most advanced, supposedly unsinkable moving object of its time end up at the bottom of the Atlantic in under 3 hours?
It's the question that just never goes away.
Yeah.
And I think for most of us, the answer has always seemed pretty simple. You know, big ship, big iceberg, big hole, bad luck.
Right.
End of story.
If only it were that simple. The science, the hard science tells us that the big hole theory is just, it's wrong. And the bad luck theory is, frankly, insufficient. What happened that night was a perfect storm. It was a conspiracy of specific atmospheric anomalies, of microscopic manufacturing flaws deep inside the metal of the ship, and, just violent physics that we are only now, with modern tools, really beginning to understand.
So let's lay out the roadmap for this investigation. We have, 4 main pillars? 4 suspects we need to interrogate.
That's a good way to look at it.
First, there's what I call the internal suspect, this theory that a massive coal fire was raging inside the ship, weakening the hull before it even left port.
A very popular theory right now. It gets a lot of headlines. But we're going to test it against the simple laws of thermodynamics.
Okay. Then we move to the external suspect, the atmosphere itself. We're going to look at an optical illusion, a mirage, that may have literally camouflaged the iceberg and blinded the lookouts.
This is the mirage theory, and honestly, it's mind-blowing, and it explains so much. Not just why they didn't see the ice, but why that other ship, the Californian, never came to help.
Then we get to what you call the smoking gun, the microscopic flaw in the ship's rivets. This is where we get into the nitty-gritty of why the ship unzipped like a cheap jacket. And finally, we're going to look at the body, the wreck itself. The violent physics of the breakup, which turns out to be very, very different from what we all saw in the movies.
It's a journey that's going to take us from the microscopic grain of a single rivet all the way to the macroscopic currents of the North Atlantic.
All right, let's start with that fire. This theory, I feel like I'm seeing it everywhere lately. Documentaries, articles. Yeah. The headline is always something like, Titanic sunk by fire, not ice.
Right. This is the bunker fire theory. It's been around for a while, but was really popularized recently by a journalist named Sinan Maloney and a fire science expert, Dr. Guillermo Rain.
And the core of the argument is what, exactly?
The core claim is that there was a coal fire in one of the ship's massive coal bunkers, specifically Coal Bunker W, which was in stokehold number 9, boiler room 5.
Just to orient us, where on the ship is that? Is it near the front, the back?
It's deep in the belly of the vessel, on the starboard side, sort of in the forward half of the ship. The theory goes that this fire started while the ship was still in Belfast, or maybe Southampton, and that it raged for about 10 days, smoldering away, leading right up to the disaster.
10 days that's a long time for a fire to be burning on a brand new ship without anyone really panicking.
Well, that's the thing with coal bunker fires. They can smolder deep inside a pile of coal without being obvious. But the proponents of this theory, they argue this wasn't just a smolder. They argue it reached temperatures of 1,000 degrees Celsius.
1,000 Celsius? What's that in Fahrenheit?
That's over 1,800 degrees Fahrenheit.
That is incredibly hot. I mean, that's getting near the melting point of some metals.
Exactly. And the argument is that this intense heat, just blasting away for days against the steel hull plates in the internal bulkhead, it changed the metallurgy of the ship. It made the steel brittle. It weakened it. It basically cook the strength right out of it.
So the theory is, when the iceberg grazed that specific spot on the starboard side, the steel was already compromised. It was pre-damaged.
It was weak. It didn't stand a chance. The iceberg was just the final push.
On the surface, that sounds plausible. Fire weakens metal, we know that.
It does. But this is where we have to bring in the rebuttal.
Right.
Because historian Tara Bay has done some absolutely incredible forensic detective work on this, and she uses something surprisingly mundane to dismantle the whole theory.
Which is?
The swimming pool.
The swimming pool.
The first-class swimming bath. This is one of my favorite pieces of historical logic.
Yeah.
You have to look at the ship's blueprints, the general arrangement plans. They are the anatomy of the ship.
Okay.
If you look at where coal bunker W is located, and then you look at what is directly on the other side of that specific steel waterproof bulkhead.
It's the first-class swimming pool.
Correct, the swimming pool. Now let's just apply some really basic physics here. Thermodynamics 101. You have a fire supposedly raging at 1800 degrees Fahrenheit on one side of a 1-inch thick steel wall. On the other side of that same steel wall, you have a large tank filled with salt water.
And steel is a conductor. A very, very good one.
An excellent conductor of heat. The bulkhead is basically the bottom of a giant frying pan. If you heat a frying pan to 1800 degrees and then pour water into it, what happens?
It flashes to steam instantly. It's violent.
Precisely. If that fire had been burning at that intensity or anywhere near it for days, the heat transfer through that bulkhead would have been massive. The water in the swimming pool wouldn't just be warm.
It would be boiling.
It would be a cauldron, a literal death trap.
And the room itself, the swimming bath area, it's an enclosed space, right? Down on F deck?
Yes, exactly. You would have had clouds of steam filling the room. The paint on the walls would be blistering, peeling off. The beautiful tile work on the floor would be warping and cracking from the heat radiating up. It would have been completely uninhabitable.
We have people who were there. We have survivor testimony about the pool, don't we?
We do, and this is where the historical record just completely crushes the high-temperature fire theory. There was a first-class passenger named Archibald Gracie. He was a writer, a historian, and a fitness enthusiast. He used the gym and the pool every single day.
Okay.
He testified under oath at the American Inquiry. He said that on the morning of the sinking, April 14th, and in the days prior, the water in the pool was comfortably warm.
Comfortably warm.
His exact words, not scalding, not boiling, not even unpleasantly hot.
Wow.
And he never reported clouds of steam or blistering paint or the floor being hot to the touch. He was a detailed man. He would have mentioned it. If there was a fire raging at 1800 degrees just a few feet away through a conductive steel wall, comfortably warm is physically impossible.
So the swimming pool essentially acts as a thermometer for us over a century later.
That's it. It sets a hard physical upper limit on how hot that fire could have been. And there's more. Or rather, a lack of more evidence.
Like what?
If the actual hull plates on the outside of the ship had been subjected to that kind of heat, they would have buckled. Steel expands significantly when it gets that hot. You would have seen a visible warp on the side of the ship.
And people would have noticed that. I mean, the press, the passengers.
Passengers, crew, the guys loading cargo in Southampton. No one reported a massive, weird-looking bulge on the side of the brand-new ship. Nobody reported the smell of burning paint or smoke in the first-class corridors near the pool.
So was there a fire at all? Or is the whole thing just made up?
Oh, no, the fire was real. We aren't denying that part. But we have to put it in context. In 1912, coal bunker fires were, well, they were incredibly common.
Really?
Yeah. It's a phenomenon called spontaneous combustion. When you pile up huge amounts of soft coal in a damp, enclosed, pressurized environment like a ship's bunker, it generates its own heat. It starts to smolder from the inside out.
So it wasn't some kind of freak accident. It was just an occupational hazard.
It was a nuisance, a routine problem. And the crew, the stokers, they knew exactly how to handle it. You don't spray water on a coal fire inside a bunker that can create steam explosions. The standard procedure was to work the coal.
Meaning you dig it out.
You dig out the burning and smoldering coal and you feed it directly into the furnaces. You essentially use the problem to power the ship.
You burn the fire to get rid of the fire.
Exactly. And the records from the firemen and the stokers, their testimony shows that They did exactly this. They worked that bunker hard all through the first few days of the voyage.
Do we know when they finished?
We do. They had completely emptied that specific bunker and extinguished the smolder by Saturday night, April 13th.
Saturday night, the night before the sinking.
Correct. The fire was out, the coal had been moved, and the bunker was empty almost 24 hours before the iceberg was even sighted.
So, the fire theory. It makes for a dramatic headline. The idea of this wounded ship sailing to its doom, but the physics and the timeline just don't hold up under scrutiny.
It's a red herring. A fascinating one, but a red herring. It distracts us from the real causes. The hull wasn't fatally compromised by fire. It was compromised by what it hit, and more importantly, by how it was built.
Okay, so let's step away from the furnaces and go all the way up to the crow's nest. We've sort of cleared the stokers. Now we have to look at the lookouts. Frederick Fleet and Reginald Lee.
These were experienced men. They had what sailors call sea eyes. This was their job.
But they were in a tough spot. I mean, no binoculars, freezing cold wind, the ship is moving at over 20 knots. But still, it's a massive iceberg. It's a mountain of ice. How do you miss a mountain until it's literally 37 seconds away from impact?
This is where we have to talk about the work of Tim Moulton. He's a historian and an author who has done what I really consider the definitive work on the atmospheric conditions of that night. And he argues that the lookouts weren't negligent, they were blinded.
Blinded.
Not by darkness, but by the air itself.
Okay, set the scene for us. We know it was freezing cold.
It was more than just freezing. The Titanic was sailing through a very specific, very volatile boundary line in the North Atlantic. She was moving from the warm waters of the Gulf Stream into the frigid, ice-filled waters of the Labrador Current.
So you have a warm ocean current meeting a cold ocean current.
And that has a huge effect on the air immediately above the water. Imagine opening your freezer door on a hot, humid summer day. You get that immediate clash. In this case, the freezing water of the Labrador Current was rapidly cooling the air directly above the surface of the ocean.
So you get a layer of freezing cold air sitting right on the water.
Right. But just above that freezing layer, you still have a layer of warmer air left over from the Gulf Stream. This creates a very specific meteorological condition called a thermal inversion.
A thermal inversion.
Normally, the higher you go in the atmosphere, the colder it gets. But here, it was the opposite. It was cold at the bottom and warmer as you went up.
And this traps things, doesn't it? Kind of puts a lid on the ocean.
It does. It creates very stable, stratified layers of air. This is why all the survivors commented on how incredibly clear the night was. They said the stars were like diamonds, that there was no haze, no fog. That's because the thermal inversion was keeping the air absolutely still.
Okay, but if it was so clear, they should have seen the iceberg sooner, not later. That seems like a contradiction.
You would think so. But this exact condition, this thermal inversion, creates a bizarre optical phenomenon called super-refraction.
Refraction, that's the bending of light.
Exactly. You know when you put a straw in a glass of water, it looks like it's bent or broken at the waterline?
Yeah.
That's refraction. Light travels at different speeds through different densities, air and water. Now imagine the atmosphere doing that on a massive scale. Because the air density was changing so drastically between the cold layer at the bottom and the warm layer on top, it bent the light that was traveling through it. Specifically, it bent the light downwards, following the curvature of the Earth.
Okay, so light is curving over the horizon. What does that actually look like to the human eye if I'm on a lookout?
It creates something called a superior mirage. And what that does is it makes the horizon appear to be higher than it actually is.
A false horizon.
A false horizon. We usually think of mirages as hot weather things, you know, that shimmering patch of water on a hot road in the desert.
Right.
That's an inferior mirage where the sky is reflected on the ground. A superior mirage does the opposite. It lifts the image of the object up. In this case, it lifted the dark line of the sea up into the sky.
So help me visualize this. I'm Frederick Fleet in the crow's nest. I'm scanning the horizon back and forth. What am I looking for?
At night, you are looking for a black shape against a star-filled sky. That's how you spot an iceberg. It's an object that blocks out the stars, but because of this super refraction, the horizon behind the iceberg, the dark sea, is lifted up.
So the sea looks like it's higher than it is.
The dark sea is visually lifted up to be behind the dark iceberg.
So it's black on black.
It's camouflage. The iceberg is physically there, but visually, it's silhouetted against a dark, false horizon of the sea. Rather than against the bright, star-filled sky, it is, for all intents and purposes, invisible.
So the lookouts are staring right at it, but the atmosphere is basically painting over it in real time.
Until the ship gets close enough and the iceberg is tall enough to finally poke its head above that false horizon line. And that is exactly what Frederick Fleet described. He said he suddenly saw a black mass that was blocking the stars. But by the time the iceberg was tall enough to block the stars above that mirage, it was less than a mile away.
Which, at 22 knots, is nothing.
It's seconds, not minutes.
That is absolutely terrifying. It's like nature created an invisibility cloak made of cold air.
And this theory, the superior mirage, it doesn't just explain why they hit the iceberg. It finally solves the century-old mystery of the SS California.
Right. The other ship, the one that was stopped in the ice just a few miles away, they saw the Titanic, didn't they?
They saw a ship, they saw lights. But they didn't recognize her as the Titanic. And for 100 years, people have called Captain Lord of the Californian a villain or incompetent for not rushing to help. But if you apply Tim Malton's atmospheric model, Captain Lord's inaction suddenly makes a lot more sense.
He was seeing a mirage, too.
Yes. The same refraction that hid the iceberg completely distorted the appearance of the Titanic. When you look at an object through a superior mirage, its light gets bent and scrambled, the vertical image gets compressed, it can look smaller, flatter, or just weird.
So the biggest ship in the world looked small.
To the crew of the Californian, the Titanic appeared to be a nearby medium-sized tramp steamer. They estimated it was maybe 5 or 6 miles away. In reality, it was the massive Titanic, more like 10 to 12 miles away. The optics literally shrank the ship.
So they didn't think, oh my God, that's the new White Star liner. They just thought, who is that little ship over there?
Exactly, and they tried to signal her. Captain Lord ordered his radio operator to warn ships about the ice, which he did, and he also had his men use the Morse lamp, a powerful light they used to flash messages.
And the Titanic saw a light, didn't they? There were reports of them seeing another ship's lights.
They saw a light, but they couldn't read the signal. And the Californian couldn't read the Titanic's reply, and the question is why? The answer is scintillation.
Scintillation, that's twinkling like a star.
It is twinkling. You know how stars twinkle. That's because their light is passing through turbulent layers of our atmosphere. Well, the extreme thermal inversion that night created extreme scintillation. The light from the Morse lamps wasn't arriving as clear dashes and dots. It was a scrambled, flickering, unreadable mess.
So the Titanic sees a flickering light and thinks, oh, that's just a masthead light bobbing on the waves. And the Californian sees the Titanic's lamp and thinks the same thing.
Total communication breakdown caused by physics.
But the rockets. The Titanic fired 8 white distress rockets. That's the universal signal for, we're in trouble. They're unmistakable. Boom, flash, white stars falling.
They did fire them, but again, the Mirage played a final cruel trick. The Titanic fired those rockets about 600 feet into the air. That's very high. But from the perspective of the Californian, looking through that distorted, lifted horizon, the rockets appeared incredibly low.
They didn't look like they were soaring high into the sky.
No. To the crew on the Californian, they looked like they were barely clearing the deck of this strange ship. They didn't look like desperate distress signals from a sinking ocean liner. They looked like, well, maybe they were company signals or private fireworks. They just looked wrong.
So it caused confusion, not alarm.
Exactly. They thought this strange small ship was just acting weirdly in a hall of mirrors. In their log, they noted that the ship seemed to be steaming away. In reality, it was sinking by the bow, which, through the distorted optics, made it look like it was simply moving away from them over the horizon.
That is just. It's a tragedy of compounding errors, all caused by the same invisible phenomenon.
It completely changes the narrative of the Californian. They weren't ignoring a dying giant. They were watching a strange, small ship acting weirdly, and they couldn't communicate with it.
So nature blinded the lookouts and silenced the witnesses. Okay, so let's get to the impact itself. Once the ship hits the ice, the clock starts ticking. For the longest time, I had this image in my head, probably from old documentaries, of a 300-foot gash. Like the iceberg took a can opener to the side of the ship.
That's the classic illustration. You see it in books from the 50s and 60s. But again, forensic science proves that completely wrong. And this is where the story gets even more disturbing because the actual damage was so small.
We know this from sonar scans, right?
Yes. Back in the 90s, an expedition led by Paul Mathias from Polaris Imaging used sub-bottom profilers. It's a type of sonar that can see through the mud that's now covering the bow section of the wreck. And they mapped the damage. There is no 300-foot gash. It doesn't exist.
So what is there? What did they find?
They found a series of 6 thin slits, small tears and punctures along the hull plates. The total surface area of the open holes, the actual space where water could get in, was only about 12 square feet.
Wait, 12. 12 square feet, that's the size of a couple of pizza boxes. Or a small doorway.
A standard interior doorway is about 20 square feet, so we are talking about a total opening that's smaller than a double door, and that sank the biggest, most advanced ship in the world.
That is impossible to wrap my head around. How does that sink a 46,000-ton vessel in 2.5 hours?
Two things: pressure and location. Water at that depth, hundreds of feet below the surface, comes in with the force of a fire hose. But more importantly, it was the location of the damage. It wasn't one big hole in one place, it was a dotted line. The damage spanned across 6 of the forward watertight compartments.
And the ship was designed to survive, what, 4?
The ship could float with any 2 compartments flooded. It could even float with the first 4 completely filled with water. She could not float with 6. It was the straw that broke the camel's back.
It's a famous zipper effect.
Exactly. The iceberg didn't slice the ship open, it popped the seams. And this brings us to the real smoking gun of the entire investigation: the rivets.
The 3 million rivets holding the whole thing together.
They are the glue. And this is where Dr. Tim Fike at NIST, the National Institute of Standards and Technology, did his work. He managed to get a few rivets recovered from the wreck site, and he decided to analyze their metallurgy to see if they played a role.
And he found a key distinction that I think most people miss. The whole ship wasn't built in exactly the same way.
Correct. The central hull, the long, straight middle part of the ship, was built using steel rivets. These were driven by massive hydraulic machines, huge presses that squeezed them into place with immense force. These were top-tier, high-pressure rivets.
But not at the bow.
Not at the bow and not at the stern. The curved parts of the ship at the front and back were different.
Why? The machines couldn't fit.
The hydraulic presses were just too huge and cumbersome. They couldn't maneuver around the tight, complex curves of the bow. So for those areas, the rivets had to be driven by hand, teams of men with heavy hammers.
And you can't hand hammer steel rivets.
Not easily. Steel is too hard. So for the bow and the stern, the areas that had to be hand riveted, they used wrought iron rivets, which are softer.
So the very part of the ship that hit the iceberg was held together by a softer metal than the rest of the ship.
Yes. But to be clear, wrought iron isn't necessarily bad metal. It was the standard shipbuilding material of the time. The Eiffel Tower is made of wrought iron. It's strong and flexible. But Fake's analysis found that this specific wrought iron had a very serious problem: the slag. It sounds like leftovers, and in a way it is. Slag is a glassy residue, a mix of silicates that's left over from the iron smelting process. In good quality wrought iron, you actually want a little bit of slag, about 2 or 3%. When the iron is worked, that slag gets drawn out into long microscopic fibers like the grain in a piece of wood. It actually gives the iron flexibility and toughness.
It reinforces it.
Exactly. But when Fake and his team put the recovered Titanic rivets under an electron microscope, they were shocked. They didn't find 2 or 3% slag. They found an average concentration of 9.3%.
9%. That's 3 to 4 times the normal amount.
And in some rivets, the concentration was much higher. And it wasn't just the amount of slag, it was the shape. In good iron, the slag is thready, fibrous. In these rivets, the slag was chunky. It was in big, glassy, sharp-edged particles.
So instead of having reinforcing fibers running through your metal, you have little rocks of glass embedded in it.
Precisely. And now we have to bring the weather back into the story one more time. It's freezing. The water temperature was 28 degrees Fahrenheit. That's -2 Celsius. It's below the freezing point of fresh water.
What does that kind of cold do to iron that's full of glassy slag?
It makes it incredibly brittle. It creates what engineers call a brittle transition. When the iceberg pushed against the steel plates of the hull, the plates themselves were strong enough. They flexed. They transferred that immense pressure and load to the rivets holding the seams together.
And the rivets should have stretched. They should have been ductile.
A good rivet would have deformed. It would have stretched a little. Maybe you let the seam open just a crack, but it would have held on. But because of that high slag content and the freezing temperature, the heads of the Titanic's rivets didn't stretch. They just popped.
Like popping the buttons off a shirt.
That's the perfect analogy. They sheared right off. Dr. Folk described it as the rivet heads just flying off like glass buttons under pressure.
And once the first rivet in a seam pops,
the load it was carrying instantly transfers to the rivet next to it, which is now carrying double the load, so it pops. And then the next one and the next one.
a chain reaction.
A catastrophic chain reaction. The seams of the ship just opened up. The plates didn't rip, they separated. The ship unzipped itself.
This feels like a massive, massive failure of quality control. I mean, Harland and Wolff were supposed to be the best shipbuilders in the world. How did this happen?
They were the best, but they were also, in a way, victims of their own ambition. We have to look at the context of 1910. They weren't just building the Titanic, they were building her two sister ships, the Olympic and the Britannic, all at the same time. These were the three largest moving objects ever constructed by human hands, all being built in one shipyard.
They stretched their supply chain until it broke.
They absolutely did. The historical records show they completely bought out their standard suppliers of best quality iron, the highest grade. They just couldn't get enough rivets. So to meet the demand, they had to go to smaller, second-tier forges, often in the Midlands of England, to fill the massive orders.
So mom-and-pop iron shops.
Shops that maybe didn't have the most experienced puddlers, those are the highly skilled craftsmen who literally stir the molten iron to work out the impurities, the slag. If you don't stir it right, or for long enough, you end up with what they call pudding iron. It's inconsistent and full of slag.
And is there any proof that this happened to the other ships? Or is this just speculation about the Titanic?
We have a smoking gun photo. In September 1911, the Olympic Titanic's older sister ship collided with a British warship, the HMS Hawke. There are famous photographs of the damage to the Olympic's hull.
Right.
If you zoom in on the gash in the Olympic, you see the exact same thing. The steel plates aren't ripped or torn. What you see are dozens and dozens of empty holes where the rivets just popped out, leaving the plates to separate.
So the same genetic flaw was in the whole family of ships.
It was. And you have to wonder, if those rivets had been steel, or even just high-quality wrought iron with 2% slag, the whole calculation changes. The plates might have dented, the ship might have sprung a few leaks, but they likely wouldn't have unzipped like they did. The ship might have taken on water much, much slower.
Maybe slow enough for the rescue ship, the Carpathia, to get there in time.
Exactly. A few percentage points of slag in a batch of iron might have been the difference between 1,500 people dead and everyone getting home with a story to tell.
That is a haunting thought. So the rivets fail, the water rushes in, and the ship begins to die. This brings us to the final act, the breakup.
The moment the ship tore itself apart.
Now, for over 70 years after the sinking, the official story was that the ship went down in one piece.
That was the conclusion of the 1912 inquiries, both British and American. And it was based largely on the testimony of Second Officer Charles Lightoller. He was the most senior surviving officer. He was on that overturned lifeboat, and he insisted she went down intact.
But other people said it split. I remember reading about Jack Thayer. He was a 17-year-old first-class passenger. He was in the water, and he said he clearly saw the ship break in two.
He did. He even drew detailed sketches of what he saw. But the inquiry preferred the more dignified version of the sinking, a clean, intact descent to the bottom. They listened to the officer, and they ignored the testimony of the teenage boy.
Until 1985.
When Dr. Robert Ballard and his team finally found the wreck, and they found it in two distinct pieces, separated by a huge half-mile-long debris field, Jack Thayer was finally vindicated after 70 years.
So we know it broke, but the question is how? I'm thinking of the James Cameron movie again, what some people call the banana peel theory. The stern rises high into the air, the keel holds on for a tense moment, then crack, a clean snap, and the stern slams back down flat on the water before sinking.
That was the best theory we had in 1997 when the movie came out, and it was based on the best evidence at the time. But the new forensic data, I'm talking about finite element analysis, and especially these new high-resolution 3D scans, they show something much, much messier. The banana peel theory implies a clean hinge, a simple snap.
And reality is rarely that clean.
The 3D scans, which researchers are calling the digital resurrection of the ship, show that the ship didn't just snap, it was torn apart. The double bottom, the massive reinforced steel backbone of the ship that failed first, the entire structure was twisted.
Twisted, not just broken.
Imagine wringing out a wet towel. The forces weren't just simple up and down bending forces, they were torsional. As the stern rose out of the water, it wasn't just lifting, it was twisting sideways. The metal was shredded. It wasn't a clean break. It was a violent, catastrophic tearing of steel plates, pipes, decks, and wiring.
And this explains the huge difference between the condition of the bow and the stern on the ocean floor. I've seen the wreck maps. The bow is, it's damaged, but it's recognizable. It looks like a ship. The stern looks like a bomb went off inside a scrapyard.
That's the physics of the descent, and this is a really gruesome bit of fluid dynamics.
Explain it to us. Why did the bow survive the trip to the bottom so well?
The bow filled with water relatively slowly as the ship sank. By the time the bow went completely under the surface, it was fully flooded, fully equalized. It was a solid object full of water. So it glided down. It actually hydroplaned like a submarine for 2.5 miles. It hit the bottom at a shallow angle and buried its nose deep in the mud, but it stayed structurally intact.
And the stern.
The stern was a completely different story. It did not flood gracefully. It was pulled under while it was still full of air.
The air pocket.
Massive air pockets. Think about it. The aft cargo holds, the refrigerated provision rooms, the massive galleys and kitchens, the enormous open spaces of the first-class dining saloon and reception rooms. They were all sealed compartments full of air.
And water pressure is immense.
It increases by 1 atmosphere, about 15 psi, for every 33 feet you go down. Within seconds of the stern going under, the pressure on the outside of the hull was immense, but the pressure inside was still just normal, 1 atmosphere sea level pressure.
An implosion.
A catastrophic, violent implosion. The water crushed the hull inward. It happened incredibly fast. The air pockets collapsed, ripping the steel plates apart from the inside out, blowing debris everywhere. That confetti field of steel and debris we see between the bow and the stern, that's the result of the stern imploding on its way down.
So it wasn't the impact at the bottom that destroyed the stern, it was the water crushing it on the descent.
Exactly. It was mangled and destroyed before it even hit the seafloor, which explains perfectly why it's just a heap of unrecognizable twisted junk compared to the majestic, ghostly bow.
It's such a brutal image.
Yeah.
And the violence hasn't stopped, has it? Because even now, the ship is still disappearing.
The autopsy isn't over. The decomposition is happening as we speak. When you see pictures of the wreck, you see it's covered in what look like icicles made of rust. They call them rusticles.
Right.
Those aren't just simple rust formations. They are actually living communities. It's a species of bacteria that was discovered on the wreck. It's called RMS Titanic.
They named the bacteria after the ship.
They did, because this bacteria loves to eat the Titanic. These are extremophiles, organisms that thrive in extreme environments. They are literally eating the iron of the ship. They consume the steel, they metabolize it, and they excrete it as rust, which then dissolves into the ocean currents.
So the ship is literally being digested.
It is. The bacteria are returning the Titanic to nature. They are turning 46,000 tons of steel back into microscopic iron ore particles. Estimates vary wildly, but the wreck is collapsing. The gymnasium roof has fallen in. The famous bathtub in Captain Smith's cabin is gone. In another 15, maybe 30 or 40 years, the structural integrity will fail completely. The ship will collapse into a rust stain on the ocean floor.
It's the final phase of the disaster. From the iron mine, to the forge, to the ship, to the bottom of the ocean, and now back to the elements.
It brings the entire story full circle.
You know, when we started this autopsy, I thought we'd be talking about who made what mistake. You know, who steered the wrong way, who didn't bring the binoculars. But this feels bigger than that.
It's not about a single mistake. It's about a system failure, a cascade.
That's the takeaway for me. It wasn't just iceberg right ahead. It was a conspiracy of factors.
It was the absolute perfect storm. You needed every single one of these seemingly unrelated elements to line up perfectly for the disaster to happen.
Let's just list them off. You needed that specific thermal inversion to hide the iceberg in a mirage.
Right. If the air is mixed normally, they see the ice a mile or two away, they turn, the ship is safe.
You needed the shipbuilding boom, the supply chain crisis, to force the use of that high slag iron.
If those rivets in the bow have 2% slag instead of 9, they stretch. The seams hold. The pumps keep up. The ship stays afloat long enough to be rescued.
You needed the freezing water to turn that bad iron into glass at that exact moment.
If the water is 10 degrees warmer, the metal stays ductile. It bends, it doesn't break.
And you needed that same optical illusion to blind and confuse the crew of the Californian.
If Captain Lord sees the Titanic clearly and understands those rockets, he comes. He's only a few miles away. He saves everyone in the lifeboats and probably many more.
If you remove any one of those rivets from the timeline of that night, the Titanic is just a footnote. It's a ship that arrives in New York a day late with a big dent in the side and a crazy story to tell.
We would not be talking about it today. Its name would be forgotten, just another old ship.
It really makes you think about the complex systems we all rely on today. I mean, what are the hidden rivets in our modern world? What are the microscopic flaws, the unseen variables hiding in our technology or our supply chains, just waiting for the right temperature, the right pressure, the right perfect storm to unzip everything?
That is the ultimate and I think timeless lesson of the Titanic. Hubris isn't just about building something big and calling it unsinkable. Hubris is assuming you've accounted for every variable. The Titanic teaches us that sometimes the smallest, most overlooked flaw, a piece of slag the size of a grain of sand, conspire with nature to bring down the greatest creations of man.
Check your rivets, everyone. And thank you for joining us on this deep dive into the cold, hard science of the Titanic. Hopefully, the next time you see that iconic ship, you don't just see the romance, you see the physics.
See you next time.